Hi there. Welcome to our cloud security project demonstration. Our team's goal was to design and implement a secure, resilient, and compliant cloud environment on AWS for a financial services application. I'm Farazuddin. I implemented the network and network protection layer, which forms the backbone of our AWS environment. Rishab handled the storage services, including S3, Glacier, DynamoDB, and RDS. Yasif focused on security monitoring and protection, implementing CloudTrail, CloudWatch, GuardDuty, AWS Web Application Firewall, and AWS Shield. Arham took care of identity and access management and service level considerations. In this video, each team member will showcase their component implementation and explain its role in achieving a secure and compliant cloud deployment. We'll start with the network layer, including the VPC, subnets, gateways, route tables, security groups, network ACLs, and our network firewall. Then we'll move on to storage, security monitoring, and finally IAM and operational safeguards. Let's begin with the network and network protection layer. I'll walk you through the design, configuration, and purpose of each component in our AWS Virtual Private Cloud. To start, I created a virtual private cloud named Project VPC. A VPC is like a private data center inside AWS. It gives us full control over our network range, subnets, and routing. By isolating our resources from other AWS users, the VPC forms the foundation for our entire network architecture. It's where all our subnets, gateways, and security controls connect. Inside the VPC, I created 4 subnets, 2 public and 2 private, each distributed across 2 availability zones for high availability. The public subnets host components that need internet access, like Bastion hosts or load balancers. The private subnets host sensitive resources like databases or internal application servers that shouldn't be exposed directly to the internet. The separation of public and private zones is a key security design principle in cloud architecture. Each subnet is connected to a route table, which defines how traffic moves within and outside the VPC. I created 5 route tables to handle different routing scenarios. The public route table sends all outbound traffic to the internet gateway, while the private route table routes traffic through the NAT gateway instead. This design ensures that private instances can reach the internet safely for updates or API calls, but external users can't directly reach those instances. The route tables also manage local routing between the subnets within the same VPC, keeping everything internally reachable. The internet gateway connects our public subnets to the internet, allowing public-facing services to be accessible from anywhere. The NAT gateway, on the other hand, is used by the private subnets. It allows outbound traffic, for example to download updates, but blocks any inbound connections, adding another layer of protection for private resources. I implemented 2 key types of firewalls, network ACLs and security groups. Network ACLs operate at the subnet level and control traffic entering or leaving the subnet using numbered rules. They're stateless, so both inbound and outbound rules must be defined. Security groups, on the other hand, are applied directly to instances and are more stateful, meaning if inbound traffic is allowed, the return traffic is automatically allowed. For example, in my security group configuration, secure shell access is limited only to my IP address, while HTTP and HTTPS are open only to the load balancer or specific internal services. Together, these 2 layers form a strong network security boundary. On top of those security layers, I also deployed an AWS network firewall. This provides deep packet inspection and allows centralized control over advanced rules such as intrusion detection or content filtering. It acts as an intelligent firewall between subnets or VPCs, giving us enterprise-level visibility and control over the network traffic. This step was important to demonstrate how AWS supports defense in depth, multiple layers of security at different points in the network. Overall, this network setup creates a secure, segmented, and scalable environment. It combines isolation, controlled connectivity, and multiple layers of security, from subnets and gateways to firewalls and VPNs. This foundation supports the other components of our cloud system and demonstrates how AWS networking principles can be used to build a secure cloud architecture.
Hello, my name is Yasser Farouk, and in this presentation, I'll be demonstrating my configuration for the Security in AWS section for our Cloud Security Assessment 3 project. So my implementation here focuses on the key security layers in AWS, including CloudTrail, KMS, S3 encryption, Event Bridge automation, and guard duty threat detection, which together establish a defense in depth environment. So throughout my process, I've documented all my steps with labeled figures, and I'll be referring to the various figures throughout my documentation for this recording. All right, so the first step was to create a customer managed KMS key with an alias finance security key. As shown in these figures here, this key is symmetric and configured to encrypt and decrypt log data. I also assigned myself as the key administrator, and added CloudTrail Service Principal as a key user. This ensures that all audit logs are written to S3, are encrypted at rest, and can only be accessed by authorized entities. So next, I configured an S3 bucket as the log storage location for CloudTrail. As shown in these figures, public access is completely blocked, versioning is enabled, and the bucket uses SSE KMS encryption with our KMS key. I also enabled object lock in governance mode for 1 year to make the logs immutable. These settings ensure log integrity meet APRA CPS 234 requirements for data protection. And this is also supported by Figure 9. Alright, so the third step was to create a CloudTrail trail named Finance Security Trail. These figures show that it applies to all AWS regions, captures management read and write events, data events for all S3 and Lambda functions, and enables insights for API error and call rates. Log file validation and KMS encryption were also activated, guaranteeing that every API action is recorded, encrypted, and verified for authenticity. Alright, so to automate alerts, I created an event bridge rule called Finance Risky Actions to SNS and an SNS topic named Finance Security Alerts. The event pattern shown in these figures below targets high risk API actions such as stop logging, delete trail, create user, and attach user policy. Yep. And when this is triggered, the event is routed to as SNS topic, which emails subscribed administrators. This is shown as I received an email upon triggering. This configuration forms a response component of the NIST cybersecurity framework. I then enabled Amazon Guard Duty for continuous threat detection. These figures show the Guard Duty dashboard in the Sydney region, confirming that the service is active with modules S3 protection, EKS protection, and malware protection for EC2 switched on. Guard Duty continuously analyzes CloudTrail events and VPC metadata to identify unauthorized access or reconnaissance activity. So to extend detection to stored data, I enabled Guard Duty malware protection for S3. As shown in these figures, the configuration links in the CloudTrail log bucket tag scan objects and creates a service role named Guard Duty S3 malware scan role. The status indicator shows the protection plan is active, ensuring that every new object uploaded to the bucket is automatically scanned for potential malware. Finally, I verified the configuration by uploading clean test files to the bucket. As shown in these figures, GuardDuty executed scans with no findings, confirming that the system is functioning in a clean environment. So this is the test file that I uploaded to trigger a scan. It was successfully uploaded, and this was the scan result. So although the malware scan didn't show up on GuardDuty findings, the S3 object tag displays malware scan status equals no threats found, which provides verifiable evidence of automated malware scanning. So in summary, the configuration combines visibility through CloudTrail, confidentiality and integrity through KMS, versioning and object lock, and automated detection and response through Event Bridge, SNS, Guard Duty, and S3 malware protection. Overall, this stack implements a practical defense in-depth model aligned with the NIST cybersecurity framework.
Hi, my name is Rishabh Sharma, and I'm going to be demonstrating my part of the cyber cloud security project. I've implemented our organizational policies in AWS, which includes guardrails, centralized logging and configuration, threat detection, and hardening storage services by KMS, and backups. First, I structured the organizations into dedicated organizational units to separate environments. I put in infrastructure, non-production, production, sandbox, and security. And I also attach service control policies to block public S3, force TLS, and restrict the region to reduce the attack surface and keep services within policy. This is one of the service control policy. I also enabled CloudTrail in the region with log file validation, KMS encryption. Where is the entry for it? And bucket versioning with default SSE KMS. Our event history shows our recent actions over here, performed by any of the cloud service account. This is the immutable audit trail of who did what, when, and from where. Now coming to AWS config, I turned on AWS config so every resource change is recorded. The dashboard shows the recorder is active, and I added some baseline rules like Cloud Trail enabled and S3 encryption enforced, default security group closed, so I can see some real compliance status and remediate the drift quickly. Uh, Moving on to threat detection, I used guard duty to enable. I used guard duty to enable detect activities over the AWS services. Security Hub aggregates finding and benchmarks against AWS foundational security best practices. I set auto enable for new controls to keep posture current. Moving on to the storage services. For storage services hardening, S3 buckets are private by default with block public access and versioning. Default encryption uses are KMS CMK. The bucket policy denies any non-TLS request and denies upload that are unencrypted with the correct KMS key. This enforces encryption from clients. And I've also updated the lifecycle rules, which the lifecycle policies transition older data to Glacier and deep archives for cost-effective retention. Moving on to the tables, the Dynamo tables. Uh, these tables are encrypted with KMS and have a point in time recovery enabled for 35 days restore. For RDS, instances run in private subnets, which are publicly accessible, publicly accessible is off traffic and is restricted via security groups. Storage is KMS encrypted and backups are retained per policy. Credentials are stored in the secrets manager for safer access and applications. Uh, Moving on to the backup, I centralize backups with AWS Backup, a KMS encrypted vault, a daily plan with retention settings, and tag-based assignments to RDS and DynamoDB, which does a pretty good job at backup execution. In summary, I transformed policy into enforceable controls, guardrails, auditable logging, continuous configuration visibility, active threat detection, and secure compliant storage with backups.